Okay, so we know that water freezes at temperatures below 0 Celsius. How does the entropy chain of the water change when it goes from a liquid to a solid? It becomes less disordered, right? But the process is spontaneous, right? It happens without any input of effort or energy or anything. The second law of thermodynamics says that for any spontaneous process, the entropy of what increases? The universe. So when water freezes below 0 degrees Celsius, its entropy decreases. But still, the entropy of the universe must increase. That makes sense? We've got two things where the entropy can change. So we have to distinguish between the system and the surroundings. So we're going to think about the water as the system. If that water that's, freezing below 0 is the system, what's the surroundings? Everything else, technically the rest of the universe. Usually we can just consider things nearby, but technically the rest of the universe. We call it the surroundings, right? So the change in entropy for the universe is going to equal the change in entropy for the system plus the change in entropy for the rest of the universe, the surroundings. So the entropy for the system can go down as long as the entropy of the surroundings goes up by that much or more. Okay? So freezing water then, for this to be spontaneous, this must be increasing the entropy of the surroundings. Well, how's that happening? We talked about, the molecules of water, when they freeze, they're becoming more ordered. That would be a decrease in entropy. How is the rest of the universe getting an increase? It's absorbing the energy. And so entropy is the dispersal or spread of energy. So water freezing is exothermic. When you cause water to freeze, you pull heat out of it. Where does the heat go? It spreads. It's just going to spread and spread and spread, right? And so release of the energy into the surroundings increases the entropy of the surroundings. So the entropy of the system, the water freezing, is decreasing, but the entropy of the surroundings is increasing a little bit more. Does anybody have any questions about that? Now, we know that freezing of water is not spontaneous at all temperatures, right? You put some water on the counter here, is it just going to spontaneously freeze? No, it's not. But doesn't that increase the entropy of the universe? Shouldn't that be spontaneous? The size of the entropy change for the surroundings depends on the temperature. So if the temperature is greater, then we get a smaller increase in entropy. Because remember we talked about delta S being Q over T. So if we think about, the water freezing and the energy going into the surroundings, that's going to be Q. And we take Q and we divide it by the temperature. So if the temperature's high, that's going to make this positive change in entropy very small. And if this is very low, it's going to make that larger. Okay? So for our system, water freezing, right? The change in entropy for the system is going to be negative. The change in entropy for the surroundings is going to be positive, but it will be large at low temperature and small at high temperature. If this is a large number, large positive, larger than this, then the change in entropy for the universe will be positive, right? So when does water freeze spontaneously? At low temperatures, right? Where the change in entropy for the surroundings is positive and large. It has to be large enough to overcome the negative change. So graphs illustrating that. So here we have low temperature. Here's our change in entropy for the system. And here's our change in entropy for the surroundings. At low temperature, this change is bigger, and so the net change is positive. At higher temperatures, the change in energy for the surroundings is smaller. And so this doesn't change. And so when we add these together, we get a negative change in entropy. Yes? How could it ever decrease? That's a good question. That's an excellent question. How could this happen? How could this decrease? And we'll talk about that. So a system exchanging heat with its surrounding changes the entropy of the surroundings so that the heat spreads into the surroundings, or the heat is being taken out of the surroundings, which means it's being concentrated. So we can use Q for the system to quantify the change in entropy for the surroundings. And we're going to do this at constant pressure to make things simpler. So the change in entropy for the surroundings is proportional to the energy for the system. So if the system is losing energy, then the entropy of the surroundings goes up, right? System losing energy, Q would be a negative. So we have this negative in front of Q, so that if Q cis is negative, this is positive. If the system is gaining heat from the surroundings, then the surroundings are decreasing in entropy because they're losing the heat. So if Q cis is a positive number multiplied by -1, then delta S for the surroundings will be negative. Okay? This minus messes people up. It does not mean that Q is negative. It means that you take whatever Q is and you multiply it by -1. Any questions? The size of that change is related to the temperature, inversely proportional. So the change in entropy for the surroundings is proportional to 1 over the temperature. So we can say that the change in entropy for the surroundings is equal to -1 times Q for the system. Q system is negative if energy is leaving the system, going into the surroundings, divided by the temperature. If we have conditions of constant pressure and temperature, then Q for the system is equal to delta H for the system. Okay. We're going to look at this reaction between nitrogen and oxygen to form dinitrogen monoxide. We're given delta H for the reaction. Calculate the entropy change in the surroundings associated with this reaction occurring at 25 degrees Celsius. Well, we're going to use this. So the change in entropy for the surroundings is equal to negative delta H for the system divided by the temperature. And then we need the temperature in Kelvin. that's 298. Now, if we leave it this way, we're going to end up with kilojoules, and the units for entropy are joules. So we need to convert this, and one way we can do that very easily is to remove the kilo and just put in times 10 to the 3. Negative 547.65, negative 548 joules per Kelvin. Any questions? And just so you know, all of these like calculations and all this math that we're doing about entropy, these are not calculations that you're going to do a lot of in the future. We're doing these now because we need to understand what entropy is so that we can understand what Gibbs free energy is, so that we can just understand why things happen. Okay. So this says, determine the sign of the entropy change for the system. It's going to be positive, right? This is positive. We have energy coming in to the system. And so the entropy, no, wait. Yeah, we're not going to look at delta H. We're going to look at moles of gases. Here we have 2 moles plus 1, 3 moles of gas going to 2 moles of gas. Is that increasing entropy or decreasing entropy? That's decreasing entropy, right? Going from 3 to 2. So moles of gas decreasing, so delta S is negative. So I kind of fooled myself there for a minute. Looking at the system, we're not looking at delta H. That's what it's exchanging with the surroundings. So the sign of the entropy change for the system, we're going to look for things like state changes or changes in moles of gas. So then what's the sign of the entropy change for the universe? It's going to be negative. Delta S for the universe is delta S for the system plus delta S for the surroundings. And that's going to equal negative 548, just negative something for the system plus negative 548 joules per Kelvin. So the sign of the entropy change for the universe here would be negative. Should the reaction be spontaneous? No. No, it shouldn't. So here's a good question. Do biological systems contradict the second law of thermodynamics? Well, the automatic answer should be no. because it's not like a speed limit law. You can't just decide to disobey it. It's a law of nature. Everything has to obey it. But what do biological systems do? They take energy from their surroundings and they synthesize large, complex biological molecules. So plants and animals tend to concentrate energy, not disperse it. How could this be? They're taking in energy, they're concentrating the energy, but they're causing large changes, large increases in the entropy of their surroundings. So for the biological system, the change in entropy would be negative, but the surroundings are going to be positive. Everybody okay with that? Let's look at what the book says. Biological systems do not violate the second law of thermodynamics. The key to understanding this concept is realizing that entropy changes in the system can be negative as long as the entropy change of the universe is positive. Biological systems decrease their own entropy, but only at the expense of creating more entropy in the surroundings, which they do primarily by emitting heat they generate by their metabolic processes. So for any biological process, delta S for the universe is positive. And just reading this reminds me of cleaning up the house. Because I think no matter how hard you try, the entropy of your house is constantly increasing. So when my son was at camp, we emptied his room. We left the furniture. We took everything out because it was bad. And then when he came home, it's like, okay, here's your room, all clean. Let's put the stuff back in. Well, where did we put the stuff? In my office? In my clean, tidy office? What does my office look like now? It looks like my son's bedroom blew up, vomited all over it. What's my son's room look like? Well, it's a lot better than it was, right? But at the expense of my office. So that's kind of like what's going on here. So you can decrease the entropy of one thing, but the entropy of something else has to increase to offset that.